recognize?
There's usually 11, so
I'm missing 3.
but one Laura might not come. Yeah, she doesn't come too often.
Okay.
Laura and Matt's photos.
Yeah.
Okay, so we'll just get going, and then if they come in, they come. I guess they can always watch the tape or whatever. Okay, so again, we're gonna continue on this journey talking about reflectance remote sensing. Again, here's a heavy text description of what we're going to talk about, placing it in context with what we spoke about last time. Right. Also, this is on the Laulima website, so if you want to grab this PDF, it's on the Laulima website now. So last time we spoke about spectroscopy, and we basically just went through, we described what spectroscopy is, right? We are shining light of all wavelengths on a target, and then some of those photons at certain wavelengths are absorbed by the target. If they're not absorbed, they're reflected, right? And what we are going to ultimately compile is a reflectance spectrum, which shows that the peaks and the troughs in that pattern, right, which ultimately we can relate to the chemical composition of rocks on the surface of the moon. Right. So we described spectroscopy, showed you some examples, and then we went through that chain of events that relates the thing we care about, the chemistry of the surface, to a whole bunch of things which we can subsequently either measure or derive. The last point on that loop was a DN, or a digital number, and you're going to look at those in class next week. And we basically said, as long as we don't break this chain, you can take the DN and you can back calculate all the way back to an estimate of the spectral radiance that got bounced off the surface from each pixel, right? Mm-hmm. And next time we meet, not next time but the time after, there's just some simple equations that would allow you to ultimately convert spectral radiance to the number of photons at a particular frequency which arrived at the detector, right? So what we're really doing is just tracking photons, right? The derived SI unit we use is a thing called spectral radiance, but we're just tracking photons from the sun to the surface. Some get absorbed, some don't get absorbed. We collect them in a bucket and we convert it to a digital number. So the first thing we're going to talk about today is the signal. So in any scientific measurement endeavor, right, we need a signal, right? So if you're studying earthquakes, the signal is sound waves that transmit through rocks. We are going to use waves of electromagnetic radiation that propagate through space, right? So that's our signal. So I'm going to talk about what the signal is. You all know this because you're scientists and engineers, but I'll briefly go over it. Importantly, I'm going to talk about how we quantify it. So I've used words like light, radiation, electromagnetic radiation. Again, spectral radiance is the unit we use. There are a couple of other parameters that you see, and I'll note those as we go along. So we're going to build up a definition of what our signal is and have an SI unit, some words, and then some pictures in our head that describe what it looks like. As I said, we collect spectral radiance, which is basically tracing photons, and eventually we get a DM. Somebody last time, I think it was the cameraman, asked, well, we've seen these Planck curves, right? We've seen these bell-shaped curves, so what gives? In reflectance remote sensing, we don't use radiance, we use reflectance, right? So at some point we take our radiance measurement and we convert it to an estimate of reflectance, which is how we compute a spectral reflectance curve, which is what I told you was the hell which reflectance remote sensing is, right? It's loads of curves that have reflectance on one axis between 0 and 1 and then wavelength on the other. So we take spectral radiance, we convert it to spectral reflectance. So I'll just describe that process to you. And then finally, I'll just give you some high-level background into why these peaks and troughs exist in spectral reflectance curves. Okay. Pointing out a couple of the more important things which we have to bear in mind when we're studying planetary surfaces in terms of how we interpret the depth of a trough and whether a trough is at one wavelength or another. Okay, so first of all, signal. So you've all, who's not seen this before? You've all seen this before, right? So our signal is electromagnetic radiation, right, or just radiation. Strictly, you would say EMR, right? This is EM radiation, so ionizing radiation. I'm lazy and I often say light. Light is strictly electromagnetic radiation in the visible part of the spectrum, but for convenience, I just say light. Okay. Life's sometimes too short to say electromagnetic radiation, time after time. When you go home, I heat a pan of soup. I don't contrive a temperature difference across a diathermic boundary such that energy flows in a preferred direction. Right. This is how we describe light when it's moving. Right. So in remote sensing, two things. You've heard about this wave-particle duality of light, and some of you probably understand it better than I can remember it from when I learned it. The key thing in remote sensing is when light is traveling, it's very convenient to describe it as a wave. When light's interacting with matter, it's often most convenient to consider it as a particle interaction. Okay. Which goes back to stuff like the photoelectric effect, right, which cannot be explained by classical physics, considering light as a wave, but can be explained by the particle concept of light. So we have two waves which are moving in space at the speed of light in a vacuum, two fields orthogonal to each other, electrical field, magnetic field. Most of the materials we care about don't respond to the changing magnetic field. So mostly we're interested in the electrical field. Some toolbox equations. So there aren't any like terrible equations in this class, but occasionally I'll flag out what I'm going to call toolbox equations. So I didn't flag it last time, but that equation, that slide where I showed you how you can take the detector size, focal length, the diameter of the optic, the height of the platform, and you can work out the instantaneous field of view and the ground instantaneous field of view. That's a toolbox equation. First order equation you can use in designing sensors to make these measurements, which is what we're going to talk about in October. So I'm going to show you how to implement these toolbox equations. This is another one, right? So speed of light equals wavelength over frequency. Wavelength, distance between peaks, troughs, frequency, number of waveforms that pass at a fixed point in space during a period of time. These are the units we use. So wavelength is measured in meters, frequency in hertz, speed of light in those units. And then, how do we generate this thing? How do we generate a signal? So this is Maxwell's laws, right? So Gauss's law of electrostatic fields. An electric charge generates, a static electric charge generates field lines that just radiate out. Gauss's law of static magnetic fields, same thing for a magnetic field, it either goes in or it comes out, but isn't changing. Faraday's law, a changing magnetic field generates a changing electrical field, and then finally the Ampere-Maxwell law, which says a changing electrical field generates a magnetic field. So the electrical engineers in the room, if there are any, will all be familiar. How we generate a radio wave is we take an electron, or several electrons, and we bounce them backwards and forwards in an antenna, right? And it generates a radio wave. And the quicker we bounce those electrons backwards and forwards, the higher the frequency of the wave, or the shorter the wavelength of the wave that's generated. So that's the most common way that people are familiar with. The sun generates a ton of this stuff, right? Electromagnetic radiation, this is our signal. In remote sensing, we usually use wavelength to denote the spectral nature of the light. Okay. Some people use frequency. Spectroscopists use a unit called wave number, which is inverse wavelength, cm to the power of -1. So if you do that stuff, that's great, but I'm just going to talk about wavelength as the unit we use to describe different colors of light. And again, wavelength and frequency are inversely proportional. In remote sensing, if you pick up 5 different textbooks, you might see 5 different versions of this. So this, all I've done here is plotted up photon energy, frequency, and wavelength, and then put this on here. This is all real, right? But this is just, if you pick up 5 different books, you'll get 5 different versions of this classification, right? So we call this the electromagnetic spectrum. Again, important notes. So if we have gamma rays, right? Everybody's seen the Avengers. Gamma rays are bad when they're shown on humans. So these gamma rays are very, very short wavelengths, so 10 to the -14 of a meter from peak to peak or trough to trough. They're very short wavelength, which means they're very high frequency. These things are inversely related. Each photon, you can imagine light on some level, again, this thing as being a stream of photons that travel via, it can be described as a wave-like disturbance in space until you try and intercept them. And then you're kind of converting photons, in our case, into photoelectrons. But short wavelength energy, short wavelength, high frequency has rather high energy, so this is 10 to the -13 versus 10 to the -28, all the way over on the other side. So these are high energy photons. So this is why when you're talking with Peter about gamma ray spectroscopy, right? He's teaching you spectroscopy where you're probing what happens close to the nucleus of molecules and ions, right? Those electrons are close to the nucleus and therefore they're very tightly bound, right? The electromagnetic force is holding them in pretty tight. In order to get one of those electrons to jump up to a higher energy level, you have to provide it energy, and the closer it is to the nucleus, the more energy you have to provide it. So if you want to probe those electrons, you need high energy photons or gamma ray radiation. Okay. On the other end of the spectrum, radio waves are very long wavelengths, so 10 to the 1 is a whole meter, right, in terms of the wavelength, which means they're very low frequency, which means they're very low energy, which means we can safely use cell phones, and if you believe, you can safely use cell phones. You can safely use cell phones and you don't get cooked when you're in your car. These are kind of what I use. So in this part of the class, we're mainly in this part of the spectrum and this part of the spectrum. In the visible part of the spectrum from 400 nanometers, and we're going to go out in this class to about 2500 nanometers, somewhere over here, right? Again, the infrared from here to here, the terms I'm going to use are visible, near infrared, and shortwave infrared. Where shortwave infrared is at about 2 microns, near infrared is at about 1 microns, and then we've got the visible part of the spectrum, which is this what I've shown here. Okay. Again, a toolbox equation, we use this later when we start. Next month, or whatever it is, we are going to predict the number of photons that come from the sun. We're going to predict how many arrive at the surface of Pluto. We're going to predict how many get reflected. We're going to predict how many get back up to the spacecraft. We're going to predict how many the telescope capture. We're going to predict how many get transmitted through the telescope and spectrometer. We're going to predict how many the detector intercepts. We're going to predict how many get converted into photoelectrons, and ultimately we're going to predict signal-to-noise ratios for targets we care about, which is the basis for designing an instrument. Okay. So toolbox equation, the last one I showed you was this one, which included frequency, wavelength, and the speed of light. Planck's, the original Planck's law, not Planck's black body radiation law, but Planck's law. The energy of a photon is equal to constant multiplied by the frequency, and obviously you can just combine these things so that the energy of a photon equals Planck's constant multiplied by the speed of light divided by the wavelength. So just an easy way of relating the thing that I'm going to talk about, wavelength, to the energy of the photon via a couple of constants. Okay, so if people consider that boring, we're now going to get onto some really boring stuff about how we describe our signal. So all this comes from the International Commission of Illumination, 1969, which is a very big book, very boring book. So first we're going to use these two terms. So people may have heard of these terms. So first is something called spectral excitance. So we're going to denote it as m lambda, and its units are watts per meter squared per micron. Remember, a watt is a joule per second. Each photon carries a certain amount of energy, which is quantified in joules. So this first term is basically how many photons at a particular wavelength, right? Light's a stream of photons. Each photon carries energy. 1 watt is a joule per second. If we cancel out the second term, this converts to joules. And then we ultimately, using the equation I just showed you, energy equals CH over lambda. We can convert that to the number of photons. So excitance looks like this. It's basically the energy which leaves a surface over an entire hemisphere. Okay. Spectral irradiance is the same, except we denote it E lambda has exactly the same units, and instead this is the energy received by a surface from a hemisphere above it. Right. So if it's leaving the surface, of the sun, we describe it as solar excitance. If it's arriving at the top of Earth's atmosphere, we would call it solar irradiance. So in generating signal, this is useful to us. To first order, if you imagine we're tracking photons from the sun, this is what we're going to call how many arrive at the top of a planet's atmosphere or a planet's surface. Right? But you see the units don't change. Joules per second per meter squared per micron. And as I said last time, the per meter squared term is because I'm not interested in how much light lands at every point, just a unit area. And then the per micron term, I'm not interested in the red photons, the visible green photons, the visible blue photons, the infrared photons, the shortwave infrared photons. I'm interested in just the green photons. So I'm going to look in a narrow wavelength band, which is denoted by this per micron term. Again, eventually I'm going to show you how we unpack this to convert just the photon flux that arrives at our detector. How we doing? Right. Okay, so toolbox equations. So this was mentioned last time. Did people give you these equations so you can compute this, or you've already got them? Right? In the work we're going to do, where we're going to predict the performance of instruments, this is kind of the starting equation. So this is Planck's blackbody radiation law. You mentioned bell-shaped curves, and I said they're kind of bell-shaped as long as you put them on a log-log scale. Otherwise, they get weirdly peaky. So all I plotted up here is spectral radiant excitance in watts per meter squared per micron. This for a body which has a temperature about the temperature of the surface of the sun, which is about 5900 K or 5800 K, depending on which body you pick up. So these are the equations I used to generate that curve. So this is Planck's blackbody radiation law. Be careful with units. It's very easy to get out by a factor of 6 orders of magnitude over or under if you're not converting between microns and meters. Right. Okay. But if we just look at this, m lambda is what we want, and in this case, I put it in watts per meter squared per meter. Right. Again, joules per second, area, wavelength. Planck's constant is just a constant. The speed of light is just a constant. Boltzmann's constant is a constant. The only variables in this equation are wavelength and temperature. So all I've done on this curve is, in Excel, in this case, I put a load of wavelengths, and then in the next column, for a fixed temperature, I've just calculated m lambda, and then I've just plotted that up. So here I've set T to 5900 Kelvin. I've varied lambda between 0.1 and about 100 microns, and that just generates this curve for me, right, which is a Planck curve. If I wanted to compute the surface temperature of the Earth, I would substitute 5900 K for about 300 K, which is the average temperature of the Earth. I would repeat that, and I'd get a curve that looked more like that, right? Because the Earth is so much cooler. This can be inconvenient, so I've given you another version here where I've just changed the units. You see this quite often. C1 and C2 are referred to as the first and second radiation constants in textbooks, and all they are is they just rolled up Planck's constant and the speed of light and Boltzmann's constant, and you get these two values with these units, C1 and C2. Conveniently, in this case, temperature is still in Kelvin, but I've converted wavelength to meters, to microns. So the output is in watts per meter squared per micron, which is, we use microns because we're interested in, we don't use meters because the waves we care about are half a micron, right? So all I've done between here and here is simplified it a little bit and converted the units to something more realistic or reasonable for us. Everybody confident they could compute this curve for any temperatures, right? It's just that equation in Excel, 2 columns, and you can produce as many curves as those as you like. So this is the starting point, as I'll talk about. If you were doing this on exoplanets, then that curve would be different because the output of the sun you're interested in will be different. So you need to know the temperature. Okay, so say we're imagining, we're going to go through a series of steps. We're interested in working out, we're going to do some remote sensing on the Earth. So that, we talk about planets a lot, we talk about Mars and Mercury, but remember the Earth is a planet. It's an important one because fools like us live on it. So imagine we're going to design an instrument that's going to do Earth remote sensing, right? And this is our signal, right? The sun is our signal. No sunlight, no signal. So this is how much leaves the sun. We're going to go step to step. What has to happen to this energy after it leaves the sun and it arrives at the Earth? It travels a great distance, right? And it spreads. Right? So by the time it reaches the top of Earth's atmosphere, the intensity of this energy is not the same as it was when it left the surface of the sun. Right? So the first thing we're going to do is correct for that, and we're going to work out what on Earth we would call top of the atmosphere solar irradiance. Right? So the amount of light which arrives at the top of Earth's atmosphere. For Mars, you would also say top of the atmosphere irradiance. For a planet that doesn't have an atmosphere, then this is just the amount of light. I'm going to show you the amount of light that lands at the surface of the planet. which again is important. If you're doing reflectance spectroscopy at Pluto, it's miles away, and far less light is going to arrive at the surface of the planet. Again, a toolbox equation. The grey curve is what we had before. Spectral excitance leaving the sun. So remember, we had excitance on the bottom there. Irradiance is what lands, what arrives. And the red curve is an estimate of what arrives at the top of Earth's atmosphere. So you can see it's been diluted by about 4 orders of magnitude. And the way you work this out is using this equation. So the top of the atmosphere solar irradiance equals the grey curve divided by pi, multiplied by the area of the sun's disk. So you just need to know the diameter of the sun's disk or whatever, divided by the sun-Earth distance squared. So this is like 150 million kilometers, something like that. So I produce the red curve, this one, by just applying this equation to the grey curve, right? And that gives me an estimate of how much light arrives at the top of the Earth's atmosphere. Simple, right? Okay. So again, we're going to do this. Designing an instrument for remote sensing mission requires that you do this, because you have to work out, ultimately, do I have enough photons to answer my science question? And the only way you do that is by predicting how many photons you're going to have. And the starting point of that is working out what the ultimate source is. So I mentioned it, but for different planets, this is going to be different, right? So all I've done calculating here is exactly the same thing, light emitted from the sun, and I applied that same equation that I just showed you, except the only thing I did was change the value in the on the lower line, which was the planet-sun distance, right? So Mars is a little bit further away from the sun than the Earth. So apples for apples, you have less energy available for you to measure at Mars, reflected sunlight at Mars, than you do for the Earth, right? Because it's a little bit further away. I plotted here Pluto. You have 3 orders of magnitude less light available to you to do reflectance spectroscopy on Pluto than you do on the Earth. So again, you're working on one of these mission concepts, and I just showed a picture here. This is vaguely to scale, right? So the terrestrial planets are all on top of each other. Pluto's all out here at 34 AU. So this is a challenge, right? If you're going to do reflectance spectroscopy here, you are going to be photon starved. Not as starved as the astronomers are when you're talking about 5 photons or whatever it is you lot are talking about. But you're going to have far less energy, right, to make the measurement. So you may end up needing a really big optic, right, a really large diameter optic to actually collect enough light to make a valid measurement. The other thing to note, which I just forgot, okay, yeah, when you're out here, this is why you cannot use solar panels on a mission in the outer solar system, because you just do not harvest enough light to power the spacecraft, which is why you need RTGs when you're going out beyond kind of the Martian type position. And some planets have very eccentric orbits. So if you were doing a study, design a mission to go to Mercury, and somebody said, I want to map iron oxides on the surface of Mercury, and you say, okay, I can work out how many photons are going to arrive at the surface of Mercury. If you ignore the fact that the orbit of Mercury is highly eccentric, there's like a factor of 5 difference between aphelion and perihelion. Right? So if you just compute it for this case, you may find out that when Mercury is actually in this orbit, you can no longer make your measurement because you don't have enough photons. Right? So this is really important for things like asteroids, which have wildly eccentric orbits. Right? Again, it's not a difficult calculation, but you've just got to think about it. And then here, most of our planets are we have pretty circular orbits. But here's Halley, so I've just showed Halley's orbit here, and then the Icarus is this one here. So if you don't account for this varying of the distance between the planet, between the sun and the target, your mission is going to work here, and it's not going to work at all here, because you're just not going to have any photons when you're all the way out here, because this line is going to be all the way down here. People okay? You confident you could just produce these curves? Yeah, it's not hard. Excel, 2 columns, 3 columns. So these are model-based outputs. So when I show you the performance modeling exercise, these are first-order calculations that give you a good starting point for this kind of thing. You can feed in real data, and ultimately, when you get later on in the design process, you have to use real data. So as an example of what real data looks like, I've shown you this before. This is the light emitted from the sun. This is my prediction of the light which arrived at the top of the Earth's atmosphere in the red line. And then the blue line is actually a measurement of top of the atmosphere solar irradiance. So various space agencies have launched spacecraft which go above the Earth's atmosphere and then look at the sun, and then measure how much energy arrives at the top of the Earth's atmosphere. You'll see that for the wavelengths we care about, right, my model prediction is pretty good. The red line and the blue line agree. So I'm not going to be too far wrong if I use my model prediction. If I was interested in measuring, doing remote sensing at 0.2 microns, I have to use the model data, the real data, because my model prediction really isn't very good. So, as I said, what I'm going to show you is first order models, but when you really get into the weeds of it, you just replace the model prediction with an actual measured value to get a higher fidelity answer. Okay, so back to this. So we have spoken about how much energy comes from the sun, right? And at the moment we're quantifying it. At the moment we said spectral irradiance arrives at the top of a planet's atmosphere, and these are the units we're going to describe it, and the amount varies on the sun-planet distance, right? And nothing else. So it's pretty simple to calculate. We've mentioned this before, but what may or may not happen to these photons between arriving 100 kilometers above the surface of the planet and then actually landing on the planet? Might have to pass through an atmosphere, right? On the Moon, on the Mercury, on comets, does not have to pass through an atmosphere. On the Earth, we have a horrid atmosphere. On Mars, there's also an atmosphere that has to be accounted for. So yeah, the next thing we might have to do is to account for the atmosphere of the planet. So this is an example of the transmissivity of Earth's atmosphere. So this is one model prediction I just generated. So I just plotted this for the same wavelength range that we've been using. Right. Transmission is a unitless parameter. Light reflectance goes between 0 and 1. If the transmission is high, that means the atmosphere is opaque to photons, and they don't get absorbed, they don't get scattered, they don't get extinguished, they just pass right through. Right? If transmission is low, that means the atmosphere intercepts or extinguishes the photons in those rays of light, and none of them reach the surface of the planet. Yeah. So, greenhouse effect. Our atmosphere is transparent to visible wavelength photons, which is where the peak of the solar emission lies. Those photons arrive at the Earth's surface, they get absorbed, they get converted to heat. The re-emission of that energy occurs at long wavelengths, where the Earth's atmosphere is relatively opaque. Right. So these areas where we have high transmission, we call atmospheric windows, because they're transparent to the passage of light. Again, this is important for a remote sensing mission, right? If I am interested in studying, say a scientist comes to me and says, "Oh, I've discovered that this particular mineral has a really weird absorption feature at 6 microns, which tells me the answer to the universal question." Right? Let's design an instrument that measures reflected light from Earth's surface at 6 microns, and then we spend $200 million doing it. And we get into space and we find out it doesn't work. Because although energy at 6 microns arrives at the top of Earth's atmosphere, none of it penetrates the Earth's atmosphere. Therefore, none of it gets reflected from the Earth's surface. Therefore, I measure no signal. Okay. So that sounds weird, but as part of the performance modeling exercise and the design, you've got to work out, is my atmosphere transparent at the wavelengths that I want it to be transparent? It's never perfectly transparent, but as we discussed last time, if I have a number, and I know there's some noise, right, so I have to apply a correction. If my number is 95 and my noise is 5, then even if I'm 100% out on my noise correction, it's still only 1 part in 9. Right? So my correction, even if it's bad, doesn't completely screw up my ultimate calculation. That would be here, right? At these wavelengths, I still have to correct my signal. The transmission isn't 1, it's like 95%. But as long as my correction is pretty good, my final answer will be close to truth. Here, the transmission of the Earth's atmosphere is like 10%. So here, noise is most of my signal, is most of what I measure. Right? I'm not going to try and correct for the effects of the atmosphere at this wavelength, because I'm just going to do a horrible job. Because a small error in my correction translates into a huge uncertainty in my final derived number. So that's why remote sensing missions stick to these atmospheric windows. And then just as some examples, you don't care about this on the moon because it has, some people say it has some kind of atmosphere, but it has an incredibly transient exoatmosphere, just like ions hopping around on the surface of the Earth. They get heated up, they come up, they condense, they kind of fall back down. The atmosphere of Mars, people saw the Martian, right? So it varies a lot, and the main problem in Mars is all the dust that gets whipped up. And then Venus is a real pain, right? So you basically can't see the surface of Venus at a lot of the wavelengths we're talking about. There are some narrow transmission bands, which people are using on the European Space Agency NMAP mission, and also the NASA Veritas mission. So they are going to do some reflectance spectroscopy, but only in very narrow bands. There are a couple of ways that you can measure the atmosphere. You can measure it. So on the Earth, at airports all around the world, they release radiosonde balloons that travel up through the Earth's atmosphere, and they measure temperature, pressure, humidity, and a bunch of other things, and you can actually get an atmospheric profile. These were derived from a radiative transfer model. So all I did here is you fake an atmosphere, you slice it up into plane parallel layers, you give each layer a temperature and a pressure, you give a partial pressure for each gas that you care about that might absorb, you throw some aerosols in that might scatter light, and then you just say, okay, the temperature of the Earth's surface here is this, therefore using Planck's equation I can predict the number of photons that leave the Earth's surface, and then you just cascade them across each layer, working out how many get added and subtracted as you go from the bottom of the atmosphere to the top of the atmosphere. And what you get is a plot that looks like that. Right? This is why Schwei does not do remote sensing on atmospheres with planets, because this is not straightforward, and this is a major error to a lot of this work. So we're just going to go through. On the Earth, we have to consider it. So in this case, all I've done is this is the light from the sun that arrives at the top of the Earth's atmosphere, right? So we computed that with that Earth-Sun distance type equation. The red curve is how much survives the journey from the top of the Earth's atmosphere to the Earth's surface. Right? And the way I derive this red curve is just to take the grey curve, and at each wavelength multiply it by this black curve. Right? So if you look here, so let's take 0.4 microns. It was originally about 2,000. It's fallen to about 1,000 at, what was that? 234. That's because the transmission of the atmosphere is about a half. So 2,000 becomes 1,000. Right? If I pick another wavelength here, didn't really change a whole lot here. Right? So that's at about 1.5 microns, because at about 1.5 microns, the transmission of the atmosphere is nearly 1. Right? So the atmosphere doesn't extinguish much of the light. But again, converting the first curve we saw to this one is simply 3 columns in an Excel file. In this case, the third column would be these numbers as a function of wavelength, and you just multiply that curve by that curve. Okay? People happy with how smart you're being and how you could easily do this in, probably not Excel, right? I mean, I use Excel, I use IDL, you probably use Python or something like that, right? Or MATLAB or something. But pretty easy to get to this. So this is an estimate of how much light arrives at the surface of the Earth after we've extinguished some of our photons via passage through the atmosphere. The next thing is the interesting stuff. So what happens next after it's passed through the atmosphere? Go back to our chain of events.
So some get absorbed and some get reflected.
After hitting
Surface.
the surface, right? So some people care about atmospheres, right? In which case you're all about this. But we're going to talk about the surface of planets mainly. So yeah, the next thing that happens to this light is it actually hits the surface. Now, if all of the photons that hit the surface were reflected with 100% efficiency, the amount of light being bounced back from the surface would be just the red curve, right? And things would be very boring, right? What we're relying on is the fact that the thing that this light strikes the surface preferentially absorbs photons at some wavelengths but not others, right? And if you remember, what isn't absorbed is reflected, so what gets turned around in that surface interaction is going to be different to what strikes the surface. So here's just a couple of examples. So again, we've shown a few curves. This is just like the transmission curve, except it's reflectance. Again, it's a unitless variable, 0 to 1. This is the spectral reflectance of an iron oxide. So we spoke about these last time, red rocks and red dirt and stuff like that. Ferromagnesium minerals, which are very common on the surface of planets, have a lot of iron in them. In the presence of an oxidizing atmosphere or environment, the iron rusts, right, and it turns red. Hematite looks like this. It looks red because we have much higher reflectance at red wavelengths than we do at green and blue wavelengths. It's not pure red because we have a decent amount of green reflectance, therefore we get something which is more like an orange. Right. Here are a couple of maps. This is what ultimately we want to do. This is a map derived from NASA's TESS instrument. Hematite concentration, 0 to 20%. And then we just color the pixels that have a lot of iron oxide in them red, and the other ones blue, and we can map hematite on Mars. Right? So what we're doing here is just doing this. We're just detecting which pixels have that spectrum in them. And as I'll show, something about the depth of the absorption feature tracks onto the amount of hematite. And then there's another map that was produced from mini-TESS, which is an opportunity rover. So, the next step in this calculation, remember, this is priming you for how we're going to design an instrument. And to design an instrument, we have to predict how many photons we have available to measure from the things that we care about. Right? If we launch a mission to map iron oxides on the surface of a planet, then we have to know what kind of photon, how well that target reflects photons. Right? If you imagine a scientist says, if you imagine I'm a complete idiot, so I want to measure the reflectance of, I want to map hematite on the surface of the planet. And I don't bother doing this. And the reflectance of hematite is actually 0, right? It doesn't reflect any light. You could argue I could map the presence of hematite because I'm just looking for something that reflects no light. But really, I need this information, right? Because at wavelengths where it doesn't reflect much light, I'm going to be photon starved. In regions where it does reflect a lot of light, I'm going to have more photons available to me. So in reality, what you would do is you would have a 4th column in your Excel spreadsheet, which would just be these values as a function of wavelength. You'll see I've kept this axis kind of constant. You just have these values as a function of wavelength in a 4th column. You would multiply this curve by that spectrum, and at that point you would have made an estimate. You would get a new curve, which is how much light leaves the surface of Mars after it's interacted with hematite on the surface of Mars. Okay. People comfortable with that? We're just multiplying columns, going step by step.
Maybe it just went down.
So to keep this clean, for this calculation, I'm just going to assume that the target equally reflects 70% of the light, maybe, that comes across it, that strikes it at all of these wavelengths, because otherwise this curve gets a bit messy. I'll show you a real example in a little while, but we're just going to assume that the target we care about reflects 70% of the light. So now I get this red curve. This was the amount of light which arrived at the surface of the Earth. Up here. This grey curve was that multiplied the transmission, right? How much survived transmission through the atmosphere. This red curve is that times 0.7, but the reflectance curve over here. And you see it's less, right? Because I lost some energy because some of it was absorbed by the surface. 30% of it was absorbed by the surface, which is why this curve is lower than this curve. The other thing you'll notice here is all of a sudden we've got another axis, right? I've divided by magic pi. And now we've gone from irradiance to spectral radiance. You can do this at any, you can divide by pi at any time. Right, I've just inserted it here because I'm just taking you through the sequence of events. Up to this point, the light's all coming in and striking the surface. Once it turns around and starts bouncing back out, now at this point, we're not interested in all the light that comes back from that surface, right? Because the spacecraft doesn't collect all the light. The spacecraft is here or here. So there's a directionality to the light that gets reflected back from the surface. And this is partly why we convert irradiance to radiance and we change the unit. Instead of E lambda, we go to L lambda, and you'll notice watts per meter squared per micron will become watts per meter squared per steradian per micron. But this is the unit of remote sensing. Okay. Right, so when you get a satellite data set, no matter where it comes from, the DN calibration that I showed you last time, to go from DN, which is a non-number, to a derived SI unit, spectral radiance, converts you to spectral radiance first. You might have to do some dividing by 10 to convert meters to nanometers or something like that. But this is the unit that we get out. Again, confident you can do this? So what's a steradian? So as I said, we have irradiance, we have excitance. This is a picture of what our signal is. A steradian is a solid angle or a cone angle, so you know what a radian is, right? It's the angle subtended by an arc which is the same length as the circumference of the circle, right? A three-dimensional radian is a steradian, where it's basically the angle squared is equal to the area at some point on the surface of the hemisphere subtended by that three-dimensional angle. You don't have to remember that. All you need to know is that to convert spectral radiance from excitance, we just have to divide by pi. Right? This pi term, people call it magic pi. You might think, you might ask why it's not 2 pi. It's pi, but the real thing about the pi term is it basically means we can use that if we assume that the amount of light reflected from the surface doesn't change as a function of the angle that we look or the angle that we illuminate in. Right? If it does, then we have a whole bunch of other problems. Most targets we care about are rough at the wavelength of the visible and near infrared light we care about. Therefore, the amount of light they scatter or reflect doesn't vary with angle. What that means is most surfaces we look at aren't like mirrors. Right? I think we can agree rocks and dirt are not like mirrors. If we look at this carpet, the light's coming in from all directions. If I look at it from here, and then I look at it from here, neither its colour nor its brightness change. Right? If I look at your clothes, doesn't matter where I look from, right? It's still green, cyan, or whatever that is, and it didn't get brighter or darker, right? Which means it doesn't matter from where the spacecraft is, right? It will still look the same.
So when would you see something that would change with the angle?
So on Earth, vegetation. So if you think about tree canopies and things like that are really, really complex. People have used, they compute not a reflectance function, but a bidirectional reflectance function, where they look at a bunch of trees from one angle, they look at a bunch of trees from the other angle, and there's a difference in reflectance at those two angles, and they can relate that difference to differences in canopy structure. So this is one advantage of using spectral radiance. The other is that it's range invariant. Right? So I've just shown that here. If we imagine we have a source of energy here, the intensity of the light will be higher here because it's spread over a smaller area than it is here when it spreads over a larger area. But the total amount of energy transferring through this angle is constant, right? Because I'm not destroying energy or creating energy. What that means is it doesn't matter whether the spacecraft is at an orbit of 800 kilometers or 700 kilometers, I'll still measure the same radiance. Right. So the way to imagine this is, if you've lived your whole life in Hawaii, you've probably never experienced this. A fire, right? So you're in front of a fire, it's orange, right? And if you're really close, it's really hot, right? And you're here, right? If you move to the other side of the room, you're not getting burnt anymore, right? But it still looks orange, right? Its color didn't change. So that's why we use radiance. for the star people, sometimes you can be so far away from the source of light that it's sub-resolution, and then what your eye is measuring is the radiance from the star plus diluted by a background non-radiance, and in that case this kind of doesn't hold, and then you've got to do some correction, right, because you're sub-resolution in terms of the emitting point.
It's different than it changing at the angle.
That's different than it changing with the angle. So we went from excitance to radiance. We flipped this around, we divided by pi. This is the unit we're going to use, watts per meter squared plus radian per micron. The key thing from this is this. I've given you Planck's blackbody radiation law, right, which gives you m lambda. To convert to radiance, you just divide by pi, right? You can do this as long as the surfaces are rough with respect to the light that you're using to probe them. And this doesn't really matter, but if anybody asks you light spectral radiance, it's like, well, it's range invariant. People happy?
Mm-hmm.
We're gonna see how much we've got to go. Okay. So on a planet with atmosphere, the energy that leaves the surface has to go back through the atmosphere again, right? So it's a two-way trip. So just going through the sequence of events, this is the amount of light which landed at the top of Earth's atmosphere. This is the amount of light which made it to the surface of the Earth's atmosphere. This is the amount of light that got reflected back from the surface after a flat 30% had been absorbed and 70% had been reflected. This is how much survives the journey back through the same atmosphere. Right? So you'll see the amount of light available for me to measure keeps falling, right? Because I keep losing photons every time I pass this thing through something, I lose photons. Right? And I've just noted it out here. Again, it's easy. This is just columns in an Excel file or something. Top of the atmosphere, multiplied by that transmission curve, multiplied by the spectral reflectance signature, divided by pi, and then multiplied by the transmission one more time, and that gives me the spectral radiance. So that's something that we call the top of the atmosphere spectral radiance, or the at-satellite spectral radiance. So that's a very common term. At-satellite spectral radiance is basically how much arrives at the front of the telescope.
Yeah, I'm just getting confused. Okay, when the light gets reflected from Earth,
Yeah.
If I look at your graph that moves from visible to IR,
Right.
basically. So, but the IR is trapped. So how do you see? I mean, when you sense it remotely,
Yeah.
you can't see the IR unless you have the instrument to look at.
Right, so you need a detector
Yeah,
that has a band gap,
yeah, oh, okay,
right, which is narrow enough
right,
such that you can free an electron using infrared energy rather than visible energy.
okay,
Right. So this is so far we are not talking about instrument design at all.
okay.
Right. So that's one thing here. We're not talking about engineering or instrument design. We're just predicting photon flux, right? Which is the basis for working out what instrument you would design to make the measurement. So if a scientist comes to you and says, it's really important I make a measurement right here, that would lead to a very different instrument design than a scientist coming to say, I need an instrument that makes a measurement right here. Right? Because here I would be detecting a large number of high energy photons. Here I would be detecting a much lower number of low energy photons. It would also translate into different materials for the glasses and the lenses, and the further out you go, you would have to cool the detector to suppress dark current and thermal effects in the material. We'll talk about that in future classes. Okay, and satellite spectral radiance. So people are happy with that. You can do this for any planet, anything in the solar system. You could predict how much spectral radiance would be available for you to measure from any planet in our solar system for any material for which you have a spectral reflectance curve, and if there's no atmosphere, that's all you need to produce this first order estimate. Okay. So we're now going to transition into this discussion about reflectance rather than radiance, right? So when you spoke the other day, we were talking about bell curves like this, right? So you're absolutely right to point that out. mentioned it in the first thing. If I have, if your clothes don't change, and I make a measurement of the reflected light now, right? I will measure. I could work out a spectral radiance value, right, for how much I'm getting bounced back. I just need to know the exitance from these lights. I'm going to ignore this short atmospheric path. We're going to measure the reflectance of your shirt. We're going to multiply one by the other, and that tells me the spectral radiance that comes back to my eye. Right? If I turn the lights off, will I measure the same spectral radiance? Right, because no light struck your shirt, therefore no light is going to be reflected. Okay. So we see this all the time on planets. There's a correction that we make, which is the angular dependence of the light that gets reflected as a function of the angle of the sun in the sky. Right. So all I plotted here, there's a cosine term, which I think I put on the next slide. No, I didn't. I'll give you the equation. I'll put in an extra slide and re-update the PDF. But the light which strikes the top of the atmosphere varies with the cosine of the angle of the sun with respect to the surface, right? So if the sun's directly above, then we get a high flux of photons at the top of the atmosphere. If the sun is low in the sky, then we get a much lower number of photons, right? Because it's spread out over a greater area. Same thing, when you take a flashlight and you point it in the ground, you get a bright spot. When you point it at an angle, you get a larger but duller spot. Okay. So we have this cosine term. I just calculated it here for multiplying. All we do is multiply this. Actually, I probably don't. For completeness, I'll include it, but all you do is multiply this curve by the cosine of this angle. Right? And that gives you this sequence of curves. So I think I did it. That's 10, 20, 30, 60, 70, 80. I think I did it now to 80 degrees. So you see, if the sun is very low in the sky, then you get an order of magnitude less energy than if the sun is directly overhead.
So if you were like doing a calculation with a satellite that was taking these measurements, would you have to every like measurement you did calculate a different value for it because the sun itself and the satellite will be at different points?
If the sun and the satellite are at different points in the sky, right? So when people design orbits to do reflectance spectroscopy, they try and make sure you can't have the sun and the satellite at the same angle all the time, right? Because stuff's moving. But on the Earth, for example, the Landsat spacecraft I showed you with those orbits in that movie is in what they call a sun-synchronous orbit, which just means that the orbital plane precesses around the Earth at the same rate that the Earth rotates, about a degree per day, right? And in that way, they ensure that when that spacecraft goes over this building on the 1st of January, when it goes over this building again next 1st of January, the sun and the sensor are in the same position in the sky. But you're right, you do have to correct for that. You also have to correct for that if that reflectance assumption doesn't apply. You know that thing about it doesn't matter which direction I'm looking at here. In this case, we just have to correct it because this limits our signal, right? There are some other things we can cancel out, but the first point in this series of steps was to convert the light from the sun to the amount of light that arrives at the top of the Earth's atmosphere. Right? Now, this is an expression of the impact it makes. So we can calculate that. This is easy. We know where the sun is. We know where on a flat Earth, we could easily compute this angle for every single point on the Earth's surface. Right? And we could correct the amount of light which landed. These are sand dunes on Mars. And you see, this is very dark, and this is kind of bright. I promise you, this is the same material. It's just that the sun is over here, right? So this is in shadow. So the way we do this, and I'll show you the data that I'm going to correct for you when we do the lab. One of the first things we have to do is correct for this sunlight effect. And one thing I'll show you. I'll add a couple of extra slides that I didn't include. I might have them in the lab handout, actually. We convert this by including something about the position of the sun in the sky, and then also a digital elevation model of the surface of the planet. So people familiar with DEM, it's just a map which shows you how high a point on a planet's surface is related to some datum, which for Earth is typically sea level. And on that basis, if we have a map of height, we can easily convert that into a map of slopes. And if we have a map of slopes, we can easily compute how the angle of a surface changes with respect to the position of the sun in the sky. And in that way, we can vary this, which is the amount of light that strikes the surface for each pixel on the ground. There is another way that we can do that, and we spoke about it briefly in the break the other day. Quite often on the Earth, people will have a spacecraft, and it's going over and it's making measurements of the amount of light that comes back out. They will then organize field campaigns where you go in the field and you stretch out an enormous white tarp, right, a gigantic white thing. And the white thing is made of a kind of expensive material which reflects really, really well at all wavelengths, right? So like 100% reflectance at all wavelengths, so like a flat reflectance curve. If I have an image where I have that pixel containing the white tarp, which has a flat reflectance curve, and I have the pixels I care about, which contain hematite, then I look at that one and I just measure the amount of energy which the spacecraft received. And then if I just divide that by that, then I can cancel out the effects of the atmosphere and also any sun elevation angle changes, right? Because all that information is in that measurement and in that measurement. The difference between the two measurements is the difference in reflectance, which is what I care about. So I'm just dividing out to isolate the confounding factors. So we'll show, in a couple of weeks, I've got some materials and we'll put a spectrometer together and we'll just make some reflectance measurements and just show you the difference. Obviously on planets, that's not possible, right? We can't go to planets and put out big white tarps. So in that case, what we would do to do this is we would try and employ a DEM from which we could predict the angle of the surface with respect to the sun. We know the position of the sun in the sky because that's just orbital mechanics, right? And then we would run one of those radiative transfer models to characterize the atmosphere, and in that way we would back out a reasonable estimate of the amount of light which arrived back in the spacecraft. People okay? So this is just that written in another simple equation, right? So these look familiar, right? Spectral reflectance curves. This is how we describe measuring the chemistry of things without touching them on planets. Reflectance unitless here to here, wavelength in this direction, lots and lots of squiggles with troughs at some places and peaks at other places. Spectral reflectance is derived from, I've just written it as excitance here, by dividing what comes out by what goes in. Right? So this is the equation, m over E, and this is just a picture. So what we're going to assume is this is the irradiance arriving from the sun as a function of wavelength. Strikes the surface of the planet. For an opaque target, we just have this energy is conserved, we have absorption, we have reflectance, they sum to 1. Right? There are some targets, water is one where you get transmission. Right? So the sum, transmission, absorption, and reflectance sum to 1. Some targets that people care about, near leaves, can transmit light at certain wavelengths. But for rocks and dirt, they're opaque. Right? So the energy arrives in, some of it gets absorbed, that gets converted to heat, which is later re-radiated at a different wavelength. But in the first instance, in the first interaction, what is not absorbed is reflected and comes back out over a hemisphere. Now remember, we're going to make this assumption and divide by pi, which means we can put our satellite here, or here, or here, or here, and it doesn't matter, we'll still measure the same amount of light. But we're going to divide what comes out, which we measure, over what goes in, which we're going to predict. Right? And that gives us a reflectance curve because we're just normalizing. So does that answer your question from the other day? How we go from these bell curves to these kind of curves? And again, the importance of these is, as we just described, if I'm dealing in radiance and I go over this target on Mars and I'm an idiot, I'm going to write a paper that says, these dunes are so weird. One side has a composition that's different than the other, right? Which it isn't. I'm going to convert to reflectance, and then If you convert to reflectance, you'll find that this impression of topography all goes away, because I'm basically correcting for the difference in illumination. Right? The reflectance doesn't change regardless of the illumination of the target. Right? So that's why we go from radiance to reflectance. That's why reflectance curves are it for this kind of remote sensing. People okay with this? So what we've done, we've gone from the sun, we predicted the amount of spectral radiance which we could convert to a photon flux at any wavelength we care about, right, really easily, using Planck's law. We've allowed that to propagate from the sun to the top of a planetary atmosphere, simple equation. We passed it down through the atmosphere of that planet, which we may or may not have to do. We then allowed it to interact with the materials on the surface of the planet we care about. Some photons have been absorbed, others have been reflected. We flipped it back round, we've divided by pi and converted irradiance to spectral radiance. We passed it back up through the atmosphere. We've then said, well, this is what we measure, but this is subject to variations related to environmental effects. The position of the sun in the sky, the angle of the sun in the sky, and the topography of the planet. So to get rid of that environmental noise, we're going to convert radiance to reflectance, and we're going to end up with curves like this. Okay? Anything baffled? You're all smart, you're all engineers and astrophysicists, right? So this is all easy. Right, so now we can start doing some chemical mapping of different minerals on the surface of our planet. So I've just shown a few curves here of some common and not so common minerals. So beaches in Hawaii are not made of quartz sand, right? They're made of calcite sand because it's like smashed up reef. Quartz, if you're at beaches where I come from in England, they're made of quartz, right? This is quartz. The spectral reflectance of quartz is kind of boring, right? Just kind of flat. Orthoclase is a different mineral. It looks completely different, right? So orthoclase is a type of mineral, plagioclase, I think I mentioned this last time. Plagioclase is the most common mineral in the crust of the Earth, the Earth's crust. Quartz is not a very common mineral in the Earth's crust. But over this part of the spectrum, I can't distinguish them, right? Because they basically reflect the same amount of light. So that's a problem. So if somebody wants to distinguish the most common mineral in the Earth's crust from a completely kind of uncommon mineral in the Earth's crust, you're not going to build them a spectrometer which measures reflected light in this part of the spectrum, right? What you would do is recommend that they build a spectrometer that measures the amount of light emitted at about 8, 9, 10, 11, 12 microns. Because at those wavelengths, these minerals do look different. So we'll talk about that in a few weeks. That's thermal remote sensing. But look at these minerals. Olivine, so the green sand beach out South Point. Pyroxene is an incredibly common mineral in basalt. Different minerals, they both contain iron. This is an absorption feature related to photons being gobbled up by electrons in Fe2+. Right? Now, you'll notice these troughs are at slightly different wavelengths. Right? I'll just show a quick picture on a couple of slides. Iron absorbs photons at very predictable wavelengths, right? Which is based on the electron orbitals of iron, which are fixed. Right? These troughs are related to absorption of photons by iron too. They're at slightly different wavelengths because in this mineral and this mineral, the iron is in a different crystal lattice. Right? And when you take an isolated iron with a certain arrangement of electron orbitals, if you take two hydrogens, right, if you imagine two hydrogens widely separated, you shine light on both, you'll get the same emission spectrum, right? Thankfully. If you take those two hydrogen ions and you jam them together, the exclusion principle tells you that the electron orbitals can no longer be the same, right? So when you jam them together, the electron orbitals accommodate each other such that you don't violate the exclusion principle and you get a new bunch of electron orbitals, right? This is called a chemical bond. As a result, the orbitals of two hydrogens jammed together are different than the orbitals of two hydrogens isolated, and therefore the wavelength at which photons are absorbed will be different for molecular hydrogen versus atomic hydrogen. Same thing in minerals. You take an iron and you jam it in an olivine crystal, you'll get a characteristic absorption here. If you take the same iron and you jam it into this crystal, the lattice is different, so the absorption will move to a slightly different wavelength. This is to a certain extent predictable. So when people make, these are library spectra, so what people have done here is they've taken olivine crystals and they've ground it into a powder, and they've done what I did here. And I'll show you how to, oh actually here. They've done this. They've taken olivine, they've ground it into a powder, they've put it in an instrument, they've shone a known amount of light onto it. They've measured the amount of light that got reflected from it, and then they've divided one by the other. Right? And they produce this blue curve. They've done the same for peroxine, took some peroxine crystals, ground them up, repeated. And people have done this for every element, and every mineral, and every rock, and every cover type you can imagine on Earth. And they've built spectral libraries, which we'll show you next week in Envy. The processing software that we're going to show you has spectral libraries compiled by JPL, USGS, Johns Hopkins, and a whole bunch of places, where they've literally got hundreds of thousands of spectra for every type of mineral and rock you could possibly imagine. But that's that and that. Here again is iron 2 in hematite and goethite. I mentioned this. Sulfur's kind of weird, right? So sulfur looks yellow, and this spectrum shows you why it looks yellow, right? This is visible red. So we've got a ton of red light. How do I make yellow?
Add some green or absorb some blue.
Right. So I absorb blue. The reflectance is really low in the blue part of the spectrum. Right. This is, what is it, 0.7 is red. That's green. Right. So I make yellow not by just mixing red and green, by mixing equal amounts of red and green. And because it's quite a bright yellow, I'm mixing kind of a lot of red and green in equal proportions. Right. The reflectance of red and green photons by sulfur is about 80%, which is pretty high. People are happy with why olivine is green.
No. Wait. Doesn't iron like absorb mostly green and blue light?
But this is not iron oxide in dirt. This is just an olivine crystal. So we've got a whole bunch of things going on in here.
Oh.
Right. This looks green because this is blue, right? And I have low reflectance. This is red, and I kind of have low reflectance. But this is green, and I kind of have high reflectance, right? Which is why this olivine crystal looks green. This one here. Peroxine pretty similar, but it's more of a dark green. People kind of happy they get this, right? So if we can do this, if the process that I've just described, if we can do this and get to this number, then we can fingerprint any mineral we can possibly form in the universe given the starting materials. Right? The question is how well we can do it. So I pointed out some assumptions, right? I'm going to build a model of the atmosphere. We're going to have a DEM. It also depends on, ultimately we're going to talk about this next time, a couple of times, I can't remember. I have shown no error bars on these plots, right? And I've shown no error bars because there effectively is no error, because these are lab measurements where I've got the light, I've got the spectrometer, there's no atmosphere, there's no nothing, I've controlled how finely I've ground the powder up. So there's no error on here. But if you imagine doing this from space, if I was uncertain of the atmosphere, then if I had a planet which had olivine, huge swathes of olivine and pyroxene on the surface of the planet, if I had an atmosphere and it was a model-based prediction and there was some uncertainty on the model, I'd have to include uncertainty on each of these points, right? Factor in if I build a crappy instrument, right? So if I build an instrument that has a ton of electronic noise on it, right? Again, that would widen the error bar. Now, if I get to the point where the error bar is so wide that I can no longer distinguish these two curves, then I can't map every mineral in the solar system. Right? So the instrument design process, when we get onto the performance modeling next month, is doing everything I've just described. Right? We're going to choose a planet, you're going to choose something you care about. We can predict how many photons arrive at the surface of the planet, how many get absorbed, how many get bounced back out. We're then going to cascade them through a fake instrument to work out what the signal to noise ratio is at the measurement we can ultimately make. And in that, we're going to vary design parameters of the telescope and the instrument to try and increase signal to noise as much as we can, or reduce the error bars as much as we can, so that we can do this kind of work. Here's just a couple of other examples. Calcite. No, I'm not going to dwell too long, but you can just look at these. These are different types of clay minerals. Gypsum with and without water. So this is exactly the same mineral, anhydrite and gypsum, except anhydrite, as it suggests, is gypsum with no water in it. Right. So the only difference between the blue curve and the red curve is water. But it makes a huge difference in terms of the shape of the curve. As you can imagine, people are interested in this because people are looking for water on Mars, for example. Calcite, so these are the beaches in Hawaii. Dolomite, which is like the metamorphic version of calcite. So if you take calcite and you squash it and heat it, the atoms realign and re-equilibrate to a new temperature pressure environment, and they form a rock called dolomite, which kind of looks a bit like calcite, but it's just a little less bright. Okay, so we have 15 minutes left. So I'm not going to dwell too long on this because people, you know spectroscopy, right? And Tyro told you about spectroscopy, right? As I said before, if I have isolated a hydrogen atom, then it can only absorb photons of particular wavelengths or colors, right? Because of the electron orbitals which characterize hydrogen. Every single thing in the periodic table has a different number of electrons to balance out the number of protons in a neutral atom. Therefore, it has a different arrangement of orbitals, and this is a cool, I don't know if everyone's looked at this. You can generate pictures of the different orbitals for all of the elements in the periodic table, and I found it kind of cool. But everything in that table has a different arrangement of orbitals, and therefore can absorb photons of a different range of wavelengths, which is what generates the color in the universe. Right, so I'm not going to dwell on that. This I mentioned before, so just a quick chart that you can look at. Again, if we're interested in probing electrons which are close to the nucleus, we have to use high energy photons, we have to use gamma rays, which is what Peter's talking about, right? Because this electron, this negatively charged electron, is held close to the positively charged nucleus by the electromagnetic force. The closer it is, the more tightly held it is. Electrons out here are a greater distance, but they're also shielded from the nucleus, right? So it takes less energy to cause an electron to jump from here to here than it does for an electron to jump from here to here, right? To provoke that transition, we have to shine photons with a higher energy to make this one move than this one move, right? And this is, I mentioned it before, this thing about generating electromagnetic energy based on oscillating electrons. We are oscillating an electron from here to here, so a quantum leap. We add enough energy, we can cause that to go from here to here. It's further from the nucleus, we had to do work to do it. And that energy came from the photon that we shone on this thing. After about a billionth of a second, the electron relaxes back down to its original position. It gives up the energy that we gave it, and in the act of doing that, it emits a photon. And the photon has the energy equivalent to the energy that was imparted on the atom in the first place. But again, if we want to probe electrons close to the nucleus, we need higher energy. If we want to mess around with these valence electrons, or electrons which form bonds, which are even less tightly held, right, then we can use longer wavelength energy. So if we're interested in probing bonds between ions, we can use thermal infrared energy. So wavelengths of 10 microns. If you remember my second chart, 10 microns is long wavelength, low frequency, low energy. Right? But it has enough energy to cause and this is like a garbage picture, right? It has enough energy to cause electrons forming bonds to move to a different rung in the energy ladder. So different wavelengths probe different aspects of matter. I'm going to talk about this and this. Peter was talking about this and this. So finally, just for 10 minutes, I'm just going to talk about why we get these absorptive features. Right, so why do we see these troughs? And why do we see these peaks? So you can almost ignore the equations here. So everybody's familiar with this, right? The law of reflection and Snell's law. So when photons strike an index of refraction boundary, right, some will be reflected and some will be transmitted across that boundary, and the difference in angle is given by Snell's law, right? And we call this refraction. Right? It's changing direction. Okay, so what happens when we shine all of these photons from the sun on the surface of Mars? I've just drawn a little picture here, and then kind of blown this up here. Right? So what have I got here? Black lines are solar irradiance from the sun, so just a gazillion photons of all sorts of wavelengths. Here we had this was a perfect angle for specular reflection, so all of the photons got bounced back, right? So these can be measured by the satellite, right? Because they got bounced back. They don't contain any information about the grains of hematite on the surface of Mars, because none of them actually penetrated a grain, right? So this is kind of like when you look at the ocean and you get blinded by sun glitter. It's just white, right? It has no color information, it's just bright and white. Because it never actually penetrated the water. It just bounced straight off the surface without interacting with the matter. Let's take a look at this one here. So this stream of photons here strikes the surface of this grain of quartz or whatever. And according to that, we get some reflection, right? And we can measure that. But we get some refraction and photons penetrate the grain, and then they start propagating across the grain. And then they hit another index of refraction boundary, and we'll get some reflection, and we'll get some refraction and transmission across the next grain. I haven't drawn the blue lines because this gets really cluttered, right? But at each index of refraction boundary, we have reflectance and refraction and transmission across grains of sand or whatever we care about. Now, in this case, well, look at that. Some photons made it all the way back out to the surface and escaped. And I can measure these photons as well, right? Because they escaped. So the red and the blue are photons that I can measure in space. The blue photons are mirror-like reflectance. The red photons are really interesting because that's how many photons survived this random walk through all these grains of sand or calcite or hematite or whatever it is. Okay. So these things could tell me something about the properties of these grains. People heard of the Beer's law or the Beer-Bouguer law or the Beer-Bouguer-Lambert law, or you hear different versions, Beer's law, right? Really important in chemistry. Beer's law, transmission across a medium, so this is transmission, is e to the 4 pi k, which is the index of absorption, which is spectrally dependent, varies as a function of wavelength, d, which is the distance the photons travel through the absorbing medium, right? So if we have a look, these photons traveled a greater distance through absorbing medium than these photons did, right? So D is higher for these photons than it is for these photons, right? Divided by wavelength. So what this is telling me is transmission of photons from here to here, you can consider it the survival of photons, right? If I have a billion, gazillion photons that arrive at the surface here, what this tells me is how many survive this journey to escape back up to the spacecraft, right? If the distance is shorter, more will survive. The other two things in here are the index of absorption, which is kind of exactly how it says, how good is that material at absorbing light at that wavelength? If the index of absorption is really high, then the photons are going to be gobbled up really quickly, right, before they've even traveled much distance through these grains. If the index of absorption is low, then they will survive for a greater distance, and there'll be more probability of them escaping out to space. The other thing is wavelength, right? This is wavelength dependent, which is good. Because remember, we're going to collect photons and we're going to split them into different wavelengths, and we're going to count the number of photons at different wavelengths, and we're going to produce spectral reflectance curves which describe the number of photons reflected at different wavelengths. Okay, people good? So really important law. You are not going to solve this, but this is just a picture of how this process works. Have a look at that. The blue we call specular reflectance, the red we call volume reflectance, and it's the volume reflectance which is imprinting. Those photons have imprinted on them this information, which is wavelength dependent and material dependent. The index of absorption at each wavelength for olivine is different to pyroxene, is different to quartz, is different to calcite, is different for every single mineral that you might care about. Is that okay? Just quickly, as I showed you, that's not true for these, right? So what this is telling me is these reflectance curves for these two minerals are the same. What that's telling me is K is the same. K lambda is the same for both of these minerals, right? Because otherwise these curves would be offset. Right? What this is telling me is the same number of photons survive the journey through these two minerals because the absorption coefficients are the same, and they're the same at all of these wavelengths. As I said, the key here is to pick a wavelength where the absorption coefficients are different, and then you can distinguish these two minerals from each other. So people are okay with that picture. This is kind of that's kind of an important picture, right? But this explains why I have a trough here and a peak here, right?
You said that they get refracted, but then they also reflect.
At each, so Snell's law and the law of reflection, there's always some energy reflected and
So then
refracted.
could the photon escape somewhere else?
But remember, what we said is we don't care
Yeah, we don't care.
from where we look at it,
Yeah.
right? If that was and this is, I've drawn this is a billion gazillion grains of sand, right? So think about the average ensemble of the light that comes back from this. You know, I couldn't draw it better than this. But it's a good question, right? The answer is yes, but as long as we make this assumption about diffuse reflectance of light, then it doesn't matter from which direction we look. We'll always measure the same spectral composition of the light. Yeah. So now let's explain. I've written it down here, but we have a trough here, right? Because at this wavelength, the index of refraction of olivine, the index of absorption of olivine was really high, right? And what that means is when I shine the same number of photons on olivine, a relatively large number of photons did not survive their random walk through the grains of olivine. Therefore, not many photons escape the surface of this pile of olivine at this wavelength. Therefore, I didn't get much radiance at the spacecraft. Therefore, my derived reflectance is low. And that's why I get a trough. So that's why I said the interesting stuff happens in the troughs. In the peaks, what we're saying is at these wavelengths, 1.7 microns, the index of absorption of olivine is pretty low, which means olivine is transparent to photons at that wavelength. Which means at that wavelength, photons come in and they can bounce around for ages in here and eventually escape. But I don't get much imprint of the chemical composition of olivine because I'm not seeing absorptions. Okay. So is that okay for people? So this is the way to think about why these curves look like this and why we get absorption troughs and why we get reflectance peaks. Okay. I did put in a graph. So this is just that thing about the angular dependence. We have two n-member. I'll just finish this up here. I'll just go away.
You have a meeting, I don't.
It's my meeting, I can't start without it.
Yeah, exactly.
So these end members, I spoke about this diffuse reflector, doesn't matter where I look, and then the mirror light reflectance, you know, you get blinded when you're on an aeroplane, you look out the window and the sun's low in the sky. We have two end member types of reflectance that we consider in remote sensing. One would be, I do this every year. Diffuse reflectance is Lambertian, right, which means the sun comes in and I get kind of equal amounts of light back scattered across the hemisphere. In this case, you can see it doesn't matter where I look from, I'm still going to measure the same amount of light. This is delete that in your slide set. I've been meaning to delete it for about 20 years. This is not Lambertian reflectance, this is specular reflectance, right? And this is the mirror light reflectance. In this case, it clearly doesn't matter which angle I look at, right? Because if I look from this angle, I measure no light. If I look from this angle, I measure no light. If I look from this angle, I get blinded. Okay. These are end members. In nature, we get things which are part between. But as I said, as long as the surface variations, the roughness. So you can imagine, this feels smooth, but it's really rough, right? You can imagine if I got a microscope and I really zoomed in, I'd see like bumps and things in it. So as long as if you like, the amplitude of those variations is greater than the wavelength of the light I shine on it, then this assumption will hold. If the amplitude of the surface topography variations is smaller than the wavelength of the light I shine on it, then it will behave more like a mirror. And we don't see mirrors too often in nature. Right? Rocks and minerals on planets are rough. Right? So our assumption holds, which means we can just divide m by pi to get L, which makes everybody's life easier. Otherwise, we've got to do this kind of thing. Right? We've got to take the amount of energy that came in, multiply it by the transmission through the atmosphere, multiply that cosine angle, which is the angle of the sun, divide by pi, multiply by this, and we've got to correct for all these angles, the sun sensor angle. Right. Just two more things. Right. So in Beer's law, we had the absorption coefficient, we had the wavelength, we also had D, right? We had this parameter D. And I said, for a given absorption coefficient, the longer the random walk through the absorbing material, eventually you're going to lose all your photons, right? Because they're just all going to be absorbed, because D will be very, very high. These are some examples of exactly the same mineral ground up into powders which are increasingly fine, right? So they took a crystal, they ground it up into particles which were less than 60 microns, so really fine, sorry, the other way, fine and then big, small balls and big balls, small, big. What we find is for the same material, and I've just shown a couple, and we're basically doing this. We're taking something big, shining light on it, measuring the reflectance, that gives us the blue curve. We're then taking the same thing and grounding it up into small particles and repeating the same experiment, and we get the red curve, right, because it's finer. So a couple of things you'll notice from this. The trough, right, these peaks and troughs kind of stay in the same wavelength, right, which is good, because that's telling me that the index of absorption didn't change, right? It's still olivine, and KD is still the same thing, right? So the wavelength is at the same wavelength, the trough is at the same wavelength. But the fine material is brighter, right? It reflects more light at all wavelengths than the coarse material. People see that? These are the same curve, just translated up or down. Okay. And the same thing over there for chloride. So the explanation for this lies in this D parameter. So if you think about it, I said that whenever photons strike an index of refraction boundary, some are reflected, some are refracted and transmitted across, and as they're moving, as they're trucking across this olivine grain, they can be absorbed in proportion to the absorption coefficient, right? At the next index of refraction boundary, some more are reflected, some more refracted, and it travels across. Each interaction with an index of refraction boundary is an opportunity for some photons to be bounced back out of this pile, right? So if I move from this to this, you get the same photons coming in, some get reflected, they get absorbed as they pass across, but I quickly encounter another index of refraction boundary, right? Which allows another opportunity for photons to be bounced back out, and if they can be bounced back out, they can escape. And the more photons that escape, the more reflective that target will be. Okay? So that's why when you take materials and you grind them up into fine powders, they get brighter. Because if you like it, the ratio of index of refraction boundaries to distance across which absorption could take place is higher for a fine grained material than it is for a coarse grained material. So you look on the moon's kind of bright, right? Apart from the Maria, apart from the dark areas, the surface of the moon is pretty bright. The surface of the moon is made of a mineral, a plagioclase mineral called anorthite. It's not, you get a chunk of anorthite, it's not like white like you see on the moon. But what's happened on the moon is that anorthite has been bombarded over 4.5 billion years by meteorite and micrometeorite impacts, such that it's now a fine powder. And we're getting this effect, which is causing minerals on the surface of the moon to be more reflective, which is why they're so bright. So I brought your attention to this because this is an important thing for planetary remote sensing. Anybody that does not have an atmosphere in our solar system has been pummeled for 4.5 billion years by large and small meteorite impacts. And they've just smashed the whole surface up. So things that we see as rocks on the surface of the Earth can easily be pounded rocks on the surface of planets. You know, when they went to the moon and they weren't sure if it was going to sink or not, when the Eagle landed, because they suspected this had happened, but they didn't know. So people happy with that? If we take the same thing, grind it into a fine powder, the wavelengths stay the same because the absorption coefficient didn't change, it's still olivine. But overall it becomes brighter because of this increased opportunity for photons to escape, because the same photon stream encounters more index of refraction boundaries. And then finally, before my faculty start shouting at me, this is why foams are white, right? So 3 pints of beer, Guinness, bitter, and then I guess a lager or something like that. So these are different beers, right? They taste different. Black, brown, and then kind of straw colored. The index of absorption for Guinness, bitter, and lager is different, right? And that's why it looks different. The heads on the pints all look kind of white, right? And the reason for that is the heads on the pints are foams. So we have thin films of beer with nitrogen or air, right, in them. And for the same reason as before, the photons come in. The photons that strike the body of the pint, they start this random walk, and as they go from molecule to molecule, there's an opportunity for absorption and reflection. But the index of absorption of Guinness is really, really high in the visible part of the spectrum, right, with white's black, right? And it's different here and it's different here, and here we have a specular difference because this is kind of brown and this is kind of yellow. Right? But the bubbles in the head, the color is only imparted when the photons cross the absorbing medium, right? These are very thin films of Guinness, very thin films of bitter, and very thin films of lager, which means D is really small, right? So in Beer's law, D is really, really small. KD doesn't change, the absorption coefficient, but D is real small, right?
Beer's low and beer's low.
Is there a difference?
I sent an email that I'll be a few minutes late,
Okay.
so just head up. So just think of it in terms of Beer's law. Photons strike the first bubble, and they get absorbed when they're passing through the thin film, but because D is small, I don't lose many. And then they pass through the nitrogen gas, and I don't lose many. And then they hit the other side of the bubble wall, and sure, there's reflection, and there's transmission, refraction, transmission, and absorption, but because D is small, I don't actually lose many photons. The opportunity for photons to escape after being reflected from an index of refraction boundary is very high, because this is all bubbles, right? So I have many opportunities for photons to get scattered back out to my eye, right? So in this case it looks white because I'm really not seeing any imprint from the absorbing medium. And that's why foams of anything look white. So this is ocean, and it looks kind of dark blue. I promise you this is made of the same stuff, right? It's water made into bubbles. The absorption coefficient of water didn't change. What happened was I stretched it out real thin. So D is low. The opportunity for photons to get reflected back from an index of refraction boundary is high. Therefore, I get very bright, uniform reflectance from the foam. But here I'm actually seeing absorption, which allows me to fingerprint water. Okay, so I've got to go upstairs before I get shouted at. But people okay with this? Right. So next time in class, we are going to look at some real satellite images, and we'll look at some data that show you this in action. And then in October, we're going to pick this up, and we will actually start telling you how you could predict the number of photons that are reflected by an ocean on a planet by doing this kind of performance modeling. And the math doesn't get hard, it's embarrassingly simple. And I produced some spreadsheets that you can use to do it. Okay, so Peter's going to hang out with you, and Eric is. This is Eric, who is our spacecraft software engineer. So some of you may have seen him. Sorry, if you've got questions, we can just do them next week or something like that. Right.
We just don't want you to be agile. Upstairs.
I told people I'd be late.
Yeah, I told it. I've seen the email, so it's okay. 5-minute break.
Yeah, sorry, we've been going on for a while, but I wanted to get through that.
That's okay. I'm flexible. camera is working, so I guess. So we're doing two things right now. One is a brief introduction or brief preview on what we will do next Tuesday. And that also indicates that everybody has to be there next Tuesday, at least from 12 to 1 p.m. Yeah, after the lecture of Dr. Wright. Yeah, because what we want to do is to give you the tools for the Thursday exercise and lecture. And those tools are basically a geospatial system or tool, Envy, called Envy, not having Eric here to explain to you what you will do or what you will have to do at that point in time. So you have to be in class, Eric will be here, I will be here, and we will help you to get
Right, and we
things
will
done.
actually attempt to give you what you need to start working on it before you get here. So in a perfect world, you'll arrive here and you'll be all done. It's like, I'm done, it worked.
But we know that the world is not perfect. We have seen this, that we really would like to have Eric to check and see that you really are done, and if you have difficulties, to use the hour that we have next Tuesday from 12 to 1
Yeah, then I'll physically be here
to troubleshoot, so that everybody is really ready for Thursday.
The biggest aspect of that, and like we definitely want to get things primed ahead of time, is there'll be roughly, I can't remember, it's at least half a gig or maybe it's a few gig of stuff to download, and that can take a long time to some people's machines.
And
But I'll have it online ahead of time and you can download it and have it ready to go.
download it overnight, because Dr. Wright was not that very happy last time when we had to start to download the 5 gigabyte files.
Yeah, when people showed up at 12, right? Yeah, that was,
Okay, and so on. So the point is, in order
trust
to
me,
make the envy
you don't want to see.
in order to make the envy exercise useful for you, that's basically for section 2. I don't know yet. I need to think about how we deal with section 1. I'll think about it this afternoon. Everybody needs to be here next Tuesday and then also next Thursday.
Right, and our goal, and this is why we want to get this stuff available ahead of time and make sure you at least do the downloading and go as far as you can, because our goal would be to prove that you can start the software and open a file so that you know you have all the pieces that actually work. So when Dr. Wright says, now do this, you can actually do it and not go, oh, something's not working, I don't understand. So it involves, like I say, just a bunch of, it's basically one large installer. Is everybody Windows or Mac? It also works on Linux.
So I have a Windows at home. Like, I have a machine that's perfectly capable, but this is not. Like, this is basically for doing like
Like a
very
Chromebook or
basic.
something.
Yeah.
Yeah.
It
Yeah,
probably
you'll
won't
need
work
a
on it.
machine that, with an actual workhorse at some level.
I mean, I have Linux on this. I use it for really limited things, but
If you can fire up the Linux, I was going to say even with the iPad, I wonder if someone can get like a virtual box going and get a Linux running in it. But the things you'll be doing won't be that massively computational challenging.
okay.
So it's not like you need a real power horse of a computer, but it does have to have all the expected bits in place that a full Windows or a full Linux or a full Mac OS would have, because the software expects to be able to do, the graphics and the loading files and all those sorts of things. And they're standard installed. So on the Mac, it's like one of these DMGs. On Windows, it's one of the .MCSIs or whatever they are. We want to be able to just click it. We'll be okay. We all use it with network licenses, but you'll all be equipped with a dedicated license, so it will run off the network. So that shouldn't be an issue. Things I ran into before, in the Mac OS, it actually uses the X11 interface, which means that you need to install Quartz, I think it's called. So anybody who has Mac OS could get a drop on things by looking at installing the Quartz X11 tool, because it starts it up, but if it's not there, none of the like, then plot this, and then look at this image, none of that'll work. Trying to think. Yeah, it'll be a moving target. We'll see. This is part of, as we install it, we'll see
Well,
new things surprise us.
so the process will be that you will download, you will put something onto Lolima.
Right. Yeah.
Then you will get a message.
I think what I did last time is I have a separate location for the files themselves, but I put a link on Lalima,
Yeah.
and you'll just be able to go to that link, download the few key files that you need, and then you should be able to just install them. Yes.
Okay.
You'll need to know, like, when it asks you for your password because it wants to be administrator. You need to be able to know that and not go, oh, I never use my password, so I don't know. Things like that
You can try
Trip
this
us up.
over the weekend.
yeah.
If there's really a difficulty, Tuesday will be the time to
Yeah.
resolve.
I know we've had troubles with the Mac OS install. You actually have to have the administrative privileges because otherwise it doesn't run it the right way and then it doesn't work. Windows is a little more forgiving. Other than that, yeah, right now I'm waiting for them to get us the licenses. So
If I try it out on this computer and my home computer, and I just can't get it to work on this machine, would it be possible to like attend the lecture remotely through like Zoom and then work from my home computer with the
That
software?
may be an option. The other one is you work with a colleague on their computer.
Okay.
yeah, and then you can go home and try it.
Then you can repeat it or try to repeat it at home with a computer that works.
Okay.
As a matter of fact, I would recommend that you do it more than just here. Once you've been given it, then go home and really explore the space
Play
of
with
it.
it.
Like I'll try with this computer, but I'm just not that savvy with Linux personally.
That's why we have that meeting on Tuesday. That's there for get everything sorted. That's actually it's this wonderful thing. Tuesdays it's 12 o'clock, so 12:05 we'll start because there's one of those comics that were prevalent in the late 60s in California. They're not in print anymore, but I do have some copies of those. There was one about this all-American hamburger and stuff like that. And one says it's this wonderful time in the universe when everything gets done. And there is a period, and it says Tuesdays after lunch.
All right. We're good to go then. Okay,
Yeah, okay,
Yeah,
good. Thank you
okay.
so much.
bye.
All right, glad to have you for a couple of minutes because we need to do a couple of things, especially to get you all sorted with respect to your projects and especially with respect to the new project, which had a due date by October 6th. But of course, because we normally start 301 late, I have not changed the due dates and I have not pushed them forward into September or something like that. So the first due date is only important for the new project. Everybody else, as I've shown you in the stuff that I have presented or provided on Lalima, but I wanted to go through it verbally so that we all are on the same page and everybody knows what they have to do. Yeah, okay, good. So I think what I said, I'm not sure where I have this stuff actually, but so we'll have the projects ready. First, there's the new project, and we have the gamma ray and neutron project. Then we'll have the CRIPS project and the VIACES project, and we basically have everybody covered. Yeah. If there are little hiccups with the VIACES and but there are none with the CRIPS. Yeah, we will be sorting them out in the next week or so. Yeah, while I'm still here. And then, so have a look at the requirement and discuss any questions in class or send me an email. Now I want to go to those requirements, and I'm not sure where I've hidden them, but they're probably somewhere in the resources. There's the detector textbook. So. Let me see what I had there. check that one, check those out. And downloads. So let me see what we have here. All right, I think that's the one, that's the valid one, that's the number 2, but I'm not so sure. We will find out. Oh, this is about SSRs, and I need to go to the other one. Oh, I have it already here. Sorry. Going to this other one. All right. Semester project and deliverables. So the fall, in the fall we have actually 3 project options. The one is a new project, then the gamma ray neutron spectrometry project, and then the VIAC's separate sub-projects. So the new project is the one that we're really learning project processes from, because all of those that are in any one of the other projects already are advanced and have to deliver advanced or more advanced things. Yeah. So for the new project, we have normally, we vacillated between a couple of items that we would give you as a starting point. So for example, we started out with targeting 3U CubeSats because we wanted to have, and you see this on the second, in this particular class, we're doing planetary remote sensing, period. This is the heritage that comes from being at HIGP. Yeah. We will change this, it will not go away, yeah, but we will change the whole thing to more system science and systems engineering perspective. So we're moving from what we do in the introductory class to what you're doing here right now in 301 as being basically indoctrinated in planetary remote sensing. We'll tone that down, start the engineering early, and move stuff from 400 down into this class here. So it will, because that will then provide more options. The reason was because we would want to develop a payload. Normally we're assuming that for this class the 1U volume payload for a reasonable project in planetary exploration would be fine. But we figured out that that was actually too complicated for a sequence. So then we went down to where the neutron spectrometry group is right now, to the 1U CubeSat form factor. And that has already influenced the CRAPES project, is one of them. But the CRAPES people wanted to make it very complicated, so we cannot necessarily complete the CRAPES project with the current 401 class. So we need to actually do the handover. That's why some of you are actually on the CRAPES project and others are on the VIAC's project, because you will carry it through 400 and 401 to completion. But I think the neutron and gamma ray group will probably be able to finish their project to into a flight configuration, to a flight satellite by the next 401 class. So I'm confident that that's going to be the case. Yeah, so we're trying, but so it's normally say we would have to have a payload that has to be developed, 103U CubeSats. Now I have opened that up because, in a sense, you know, it's September 28th. Man, that's too early. I have opened that up to very generic things. So you don't have to develop a payload for your new project. So and I will carry that through into the next one. You can actually develop something that is somewhere in a NASA strategic priority plan. It can be for spacecraft development. It can be for anything that has to do with functionality of the spacecraft. Doesn't have to be payload. Yeah. So that means, however, that we now have to do select something, and the way I would want to move forward with that was that I'd like to see a concept paper at the very beginning. So the 201, the gamma ray spectrometer and the neutron spectrometer did do a concept paper in 201. Yeah, so they don't have to deliver that. And we actually tried to get to a systems requirements review then as well at that time. So, apologize for my spelling. There is September 28th is actually this next week, Thursday. Yeah. So the new project group has actually until September 28th to write that concept paper. And what is the requirement? I said it's the project definition paper minimum length depends on the number of so provide. So what did I say? How many standard pages? Can anybody see that?
Per group member.
Is that below?
Pardon?
2 pages per group member.
Yeah, 2 pages per student. So it's 4 pages concept paper I need to get from you guys by September 28th. Yeah. And there's 250 words, 500 words per person. And I don't care whether somebody wrote 251 words and the other one 249. I don't worry about that.
But we're combining it and turning it in as one
You're
paper,
writing
though.
a joint paper.
Okay.
You don't have to divide it. Actually, I'm always unhappy when it is divided because that happened in some groups, last semester, and then there was no coordination. Yeah, that was not intended.
Mm-hmm.
So you're supposed to collaborate on this, and
Okay.
supposed to provide a joint paper. I'm not going to ask you which letter and word you created and which letter and word another one created. So it's fine. It's in you see that there's a danger in that very generally. It has nothing to do with what we're doing right now. The danger in that is that the work that some take a free ride on this. If you have a group of 4 or 5 students, the rule is at least one of them is not carrying the weight. Well, to some degree we can carry that if it's getting really outlandish, and then we'll deal with it. And the other thing is that actually, once in a while, there's conversions. People actually start to realize that they're having not contributed, and then start to really work hard to make sure that they over-contribute for the next step. So it's all a little bit of a wash. If there's real concerns that issues arise in inequality in contributions, then I need to know about that, and you can tell me. Okay, so that was the first item. So then there are several things that I need to explain, and we can discuss that. So this is basically the outline for all of class. If you don't, if you have the concept paper is due on the end of next week, then we'll have until October 19th to do a systems requirement review. This is, I would want to repeat that. This is for the new project, and this is for the gamma ray and neutron project. They need to have a systems requirement review. For the gamma ray neutron project, it should be a joint systems requirement review, if you can. So then you can distribute the work a little bit. That's basically also a repetition of what you did, most of what you did already, and what you're learning right now in the lab, if you get to that. And then this was, I said the estimated due date is October 19th, a percent of grade, and then we are in 301. That was the oral presentation, is that correct? Or did I, I think I may have made a small mistake here. No, it's the same. Yeah, and there's a difference because now I understand what I wrote. Because the new project does more work, has at least one more item. The value of the SSR for the new project is only 10%, and for the others it's 50%. Now I understand this. Yeah. Okay. So, then we'll have time for about a month to go the next step. Now, this can be, I want to be very careful, and in this case, then the viaces and the crepes actually come in. We want to either do a delta SRR or a form of a PDR, preliminary design review. This, for the viaces and for the crepes group, is basically a repetition what others have done, but it also forces those that are on the crepes and on the viaces group to basically reinvent the PDR from what the other group has done. And that's useful because that finally helps everyone that is on the viaces and the crepes group to do their own work to understand what they're going to be doing, and what the group is going to be doing. I can evaluate that, but I can also ask your viaces and crepes peers, to assist in critiquing and evaluating the PDR. For the new project, it can be a PDR or a delta SRR. Depends a little bit how much of the research you get done and how comfortable you feel with respect to, and how good the SRR was, and how comfortable you are to get those things formulated in the form that they actually are PDR, and actually given you examples and information about what an SRR is and what a PDR is and what a CDR is, or whatever. So then what we see here, we're starting presentations only for the delta SRR or the PDR. So this is only writing, and this is a writing and an oral presentation. Because this class gives you a WI and an OC. So you need to have that oral presentation ready. All right, now the next step is either a PDR or a critical design, a CDR, a critical design review. I'm absolutely certain that 401 will do a CDR on each one of the payloads that you're involved in. And then here it depends. If you have a delta SRR here for the new project, then we will have the PDR here rather than anything else. So the issue is not to move forward through some formality. The issue is to get these things right. And the point why we do that is that determines while we have to bridge 400, because we need to bridge 400 with a Y Space Grain Consortium, extracurricular activities, so that you can go back and do your stuff and complete your things to the final capstone project in 401. So we have this PDR or CDR, and for the viaces and crepes groups, that's probably work that you will do together with the people that have to do their CDR at the end of this semester in 401, and you basically do the same thing. You will then report back here when you do your oral presentation, or your writing. Should be separate, or not necessarily, but it depends a little bit on how we. It's just that you make sure that we'll get some pages of writing from you that's actually truly from you. And then there's the final thing is on December 7th, which is the last day of classes. We will have then the presentations, our presentation. With that, you would fulfill all requirements for this course.
Is that before finals?
It's Thursday before finals. Thursday before finals week. Questions? I'm pretty sure there are questions. Yes, go ahead.
Is that on Lolima? Like that kind of stuff?
Yeah.
Okay.
I'll pull this off Laulima.
Okay.
Actually, I just downloaded it for myself because on my rather complex arrangement on my screen, I would not find it easily. Even the Finder the finding, whatever it is application or app. Sometimes a little bit confused and I don't find what I want. But anyway, I mean, I could be confused, and the finder is okay. It's okay. Yes, this is on La Lima. This is actually, I can show you where it's posted. I'm going to go back to resources. This is where I downloaded it from. I'm going to go back to resources. So I've given you 2 files outside of the weekly files, which is a detected textbook, and then all down at the bottom is the project requirements, and that's where you can find these files. Did I have anything else in here? No, that's fine. Now let's go back to this one here, because I did give you, I thought I gave you in the next thing I give you the, this was, this one, I'll take this one out, and this, that one I had. So let me go and do this. So here, you'll see what I did first is I did show, in order to, this is for the group 1 because nobody has to do an SRR anymore. So did I say you have to do an SRR? Okay. For anyone who has to do an SRR, for VIACs and CREPs I said it's not required. Did I just tell you it's required?
No, you said.
No, you,
Okay.
You said the
that.
right.
That's good.
That's fine.
Yeah.
So then we're fine. Yeah. Okay. But here is what I would like to see in an SRR. So that I did this for your benefit, and you can always ask me questions. What an SRR is. The SRR. So the concept paper is there to let me understand that you understand what you're going to be doing. So this has that can be as a free form. You just need to convince me. Yeah, that's all. And easy, you can easily persuade me. I am not too tough. And if I see something, I give it back to you. But if it's written well and it's not graded upon the stuff is not graded upon content. If I see something that needs to be discussed, we'll discuss it, and that's okay. Yeah. Okay. Good. So this is the SRR. What you need to know for the thing that you want to propose is all performance requirements, both explicit and derived, are well defined and traceable. Yeah. That's an interesting exercise. So I think we did not. Our early jobs were not that perfect, but we make up at the PDRs or so. So what it says here, there's key performance parameters, key system attributes and stuff like that. You don't have to worry about that yet because you don't know the language and know the details of how to deal with that yet. But we're wanting to make sure that at least from the step from the concept paper to this one is that you go into real details of what is required to make this thing work. Yeah. It says verification methods are identified, risk items. I only said in the preamble said only the red stuff is what you need to concentrate on. Yeah. Because otherwise we'll overload. And here is what you need to look at from the red point of view. Systems performance specifications. The team clearly demonstrates an understanding of the system requirements. That means you need to show that you really know what you're talking about. You know? The system requirements are sufficiently detailed and understood to enable functional definition and functional decomposition. That means you have enough stuff there so that we can divvy it up into finally later into engineering and other requirements that flow from this original systems requirements review. Later in the PDR, that spreads out and becomes very detailed. Yeah? And then, so requirements can be met given the plans for whatever. That's okay. I put it into brackets. Technical interfaces are inadequately defined. Only you need to show where there is technical interfaces. You don't have to define them in detail. Yeah? Including interdependencies associated with schedule, test, and configuration. Sort of a little bit not bolded. If you get there, fine, but if you don't get there, it's also okay. And then preliminary identification of all software components are completed. That I should have highlighted. That I would like to see reflected. But as far as I know what your project is, software is not that important. Yeah. But we'll come back and invite those who do detectors, whether it's VICs or whether it's radiation, gamma ray neutrons. We have to start seriously thinking about software early on. Yeah. And this came up in a discussion also with the Krebs group that actually going to do a CSLI proposal by November 17 or something like that, shortly before Thanksgiving. We have noticed that in anything we've done so far, we have absolutely lovely neglected software. And there's a reason for that, of course. Because most of you, those who are not scientists, most of our engineers are mechanical engineers, and we don't have electrical engineers in abundance that would actually make that task easy. Now, I'll talk about that in a moment. So, that's it. So I have done this for the SRR. There will do another one for PDR. Yeah. So that is available in time for those, but specifically for gamma ray neutron, we need to have the rules for the PDR. For the VICs and the Krebs, your student colleagues will have the rules of the PDR imbibed. They know it. They can help you. They can teach you if they are willing to do so. And then there's a little bit. That was this one here. So that's where I wanted to be in order to give you sort of the rundown of where we would want to be with the things that will actually provide me with gradable materials and you with grades. Any questions or comments? Oh, it's all crystal clear. Okay, so then next time you do a student evaluation, say he made the course, whatever it says. Well, I don't know the questions anymore. But anyway, so I did not do that in order for this particular purpose, because I think we need to have clarity anyway. Because I don't want to see a PDR that's not a PDR. I don't want to see an SRR that's not an SRR. I have to go give it back, and it only creates more work. Yeah. Okay. I think that is good because it's going to be sort of some preliminary understanding of this SRR to PDR environment. Eventually, even for those that do the Krebs or especially the VICs will have a CDR, I'm pretty sure. The Krebs may not. Yeah. So that prepares you for 400 as well a little bit. But I don't want to overemphasize the formality. You will have enough formality later on in 400, and then we're going into real hard work in open bench work and so on in 401. Yeah. Okay, good. So now let me. We have still a couple of minutes, and I don't want to send you home now that I have you again. I want to make sure that we understand some other things. So I have sent you I think I've shared with you 2 announcements on scholarships that are for which the applications are due early October. It's the Bowen Scholarship and the Isakowitz Scholarship. You'll find it somewhere in an email that I've sent to you outside of Lonima. Because the due date is very soon, you need to make a decision. Because otherwise it's going to be cramped. Yeah. The other thing is that I wanted to say is yes. Why do I advertise and say talk about internships? Because I think internships are a very important part of your education. You should try to get an internship at the latest in the second summer of the program. That will be actually this coming summer. Yeah. Okay. So if you're not going to go for the Bowen and Isakowitz internship, there are other internships become available later in the year. Most of them that we know of at this point in time will probably be with NASA, or another federal agency. Yeah. I haven't seen any announcements of those, but I will actually share those announcements. And then I've told you about the RD51 school success. Have I? Haven't I? You didn't, okay. So, those that are working with the Crepes group will probably have learned about it already. The Crepes detector is actually a gaseous detector. It's a so-called gem detector. I forgot, gaseous electron multiplication detector with spatial resolution options built in. That's a significant field of development in Europe and in the United States. It's actually a big physics system competition. So we basically have relationships to both the European environment and the US environment. But the Crepes group actually worked with the European environment. They got most of the information for the Crepes detector and so on from the European environment. And in particular, we were able, and this is not, I want to make sure that I will actually write about this into UH News next week or the week thereafter. We were able to get the key inventor, the key the key person that developed these detectors, Fabio Sauli, with over 600 or so publications in the field, so a significant and eminent scientist. Yeah, he gave lectures to our Crepes group last semester at 6 o'clock and 7 o'clock in the morning. Yes. But that actually led to significant exchanges. First of all, we got detectors from the CERN, from the European group at CERN, and then 3 of our students of the Crepes group of 5 applied to participate in the RD51 gaseous and micro detector or whatever school in Switzerland in November, December this year. And 2 out of the 3 got a invitation for direct participation, and the 3rd one also got an invitation for the online participation. So this is a significant success. This is actually, you need to know though also that this RD51 school is normally for graduate students. So we're doing quite well. Yeah. So that's why I'm always pushing a little bit, and telling you go the extra step, if you can. There's many opportunities out there, and everything you can do extra in an internship or applying for an extra, for summer school or for a specialist school like this one, enhances your education and your ability to go to grad school and to be successful later within the subject area that you have chosen. Yeah. Okay. So that's going to be, I'm working on it. Us notwithstanding though, a doctoral student from Sven Wassen, who's a physics professor, also got into the RD51 school. Yeah. So telling you 3 students from Hawaii, made it. So I'll make a story out of that and have it published. And that leads me to the next and last item, which is also not curricular, and I think it's okay if it's a videotape. I want to go out after the 29th, then I have a little bit of time, to ensure that we'll be advertised for the next cohort of EPET. So I'm certainly interested in getting your input into that. And there's two things we want to do in particular. We want to make sure more electrical engineers are showing an interest or actually learn that there's an opportunity, let me put it that way, to do something special. Yeah. And we want to have more computer science students to come and join us and understand that they're, because that helps us to more and better and more sophisticated and more interesting projects. So you have an idea? I'd love to go with that. Will you let me know?
I work in the advising office and we can advertise there.
You can.
I would
The
reach
point
out to
is to
the
get the right
engineering
story.
school too.
See.
Yeah.
To get the right engineer, I can handle. That's not a
Okay.
problem.
Well,
I
we
know.
have ICS students in our
Yeah.
college.
It's computer sciences in your college and the natural sciences.
Yeah.
So I need to find a good hook, to interest them. Yeah. We're building spacecraft, and the spacecraft will eventually fly. We're applying for flight opportunities. It's actually, and all research is student. How do I say that? Students have selected the research, and students will manage and operate that research. It's different from doing a research project for Dr. Wright, for example, because he wants you to do some extraterrestrial materials analysis or so. Yeah. Okay. So, it's okay. So I need to find a clever approach to sell the product. So there's another aspect for the next 201, which I can sort of pre-announce, is we're in the process of getting 3 additional courses are submitted in that environment in human spaceflight technology. So if students would want to bet on being able to get a certificate in human spaceflight technology, if they want to bet on it, because we don't have it yet, we only have approval to plan. But I think I'm confident we'll get it. Yeah. Then they should actually go into the next EPA 201 class, because the first class we would probably teach in the new branch of EPA would be the equivalent of 301. So we'll probably give it the number 310 or 311 or something like that. That would be coming up in the fall. And then by that time, we would have the certificate accepted. So that's another aspect that I need to fold into that advertisement. So we'll see. I don't know. Anyway, I kept you for very long, but I appreciate your being here next Tuesday. Just to remind everyone, because it's now on tape, next Tuesday you have to be here in order to make sure that we have an understanding that you are all ready for Dr. Wright's Thursday class, so that you can start Envy without delay and have the full benefit of the 2.5 hours of Envy studies on Thursday, the 28th of September. Okay. See, I even remembered that one. Okay, thanks so much.
Okay.